Hey folks, welcome to the webinar. Good morning, good afternoon, good evening from wherever you're joining in. Today I just want to talk about k0rdent AI and specifically how you can get sovereign AI infrastructure at scale by using k0rdent AI. So just a couple of things about me. I'm Bharath Nallepeta. I'm from the OSPO team, Open Source Program Office here at Mirantis. I have worked at companies such as Red Hat and HP before this, and I've been working in and around Kubernetes for like 4 to 5 years now. So first started as a user of Kubernetes, and then a developer of Kubernetes, adopter of Kubernetes, and yeah, I'm really excited to be here because some of the things that we're doing are like cutting edge technology, where try to merge the world of Kubernetes with the world of AI, where the future is. One thing we have to realize in today's world is that the multi-cluster, multi-cloud thing is becoming the norm. According to the survey, which I'm showing you right now, 76% of the organizations have implemented multi-cloud strategy. What that means is they have at least in enterprise, in production, running either two or more clouds. So they have like AWS GCP, Azure GCP, vSphere, and AWS, whatever combinations, right? Two or more clouds. And many of the enterprise customers definitely have more than two clouds, right? But the pressing thing over here is that only 29% of them have adopted platform engineering. So what happens is quickly we will run into a Kubernetes sprawl problem, whether you're just managing a small cluster or a small team, and let's say 5 to 10 clusters, or even production level 100 to 200 to 2000 clusters, the challenge of maintaining all this becomes really hard. And then there's the application level problem as well. So when you have all these clouds and then you have to interact with all these clouds, let's say their APIs, their storage and whatnot, right? Load balances, all these components, it becomes extremely difficult even at your application layer, the cloud native application layer, to maintain this and then to have a standardized process. So as you can see from this graph, the complexity just exponentially increases, and this becomes a real nightmare for the platform engineering team. To add to this, I can't even say future. The slide shows future, but we are living in it. This is the present already. Whatever app you have or interacted with, if it doesn't have AI already, it soon will. It doesn't even matter what industry you're from, but as long as you have anything in production, there's some sort of AI that's already coming in or will come in. So the control plane, so the entire platform engineering that we saw earlier now also has the added complexity of managing your AI models, your AI infrastructure, right? So the cloud native application problem has now becomes the AI native application problem. Then there's the other big challenge that is beyond an individual level or beyond a company level, the AI sovereignty challenge. So what this essentially means is that we all know, like the GPUs and the hardware has some real geographical and political, what do you say, a barrier, right? It's not easy to get a GPU whenever you want, depending on what part of the world you're from. So I don't want to like get too much into the geopolitics of it, but then this is the reality we live in, right? So this survey that I've put up here from CNBC and Modern Intelligence says that if you go to any of the big guys, the AWS and Azures of the world, and you request for some specific GPUs for your production enterprise level, in some cases the wait time has been 12 to 18 months. And even if you don't think about the big GPUs, even the more than medium scale GPUs also have had a healthy wait time of, or rather unhealthy wait time of like 6 to 8 months. Right. So when interviewed, a lot of executives and a lot of platform engineering teams around the world quoted that the top barrier, like 73% of them said that the top barrier for them in order to execute these AI apps and get these into production is the AI infrastructure bit, right? So it's, again, like I said, it's this challenge is not just at an individual level or a company level, it goes beyond that, right? So no matter what kind of application you write, and we hear about this all the time, right? Everybody's coding apps left, right, and center. Like you're able to get an app into the production ready state in insane times. The whole cycle has probably reduced by 1/10 of the time, if not more. And not just like some vibe coders sitting over a weekend and developing, not just that group, but even companies who have really, really worked and adopted AI tools, and then they have sort of really increased their productivity. And the wait times are, I mean, the production development cycles are much, much faster and shorter. But then now you're stuck with the challenge of AI sovereignty, right? And here's where we need to understand the infrastructure for running these AI models is a bigger challenge than the AI models themselves. The AI models were the focus of the entire world probably like 2 years ago when GPT and Gemini and Claude and all these people were competing to make the best model, possible and then available at a affordable price for the public. But that stage is gone. We've moved past that. Right now, accessing a AI model which is really good enough for production use is very cheap and easy. It's straightforward. You need to generate videos, Sora is there, and a bunch of others. You need to generate images, you have a bunch of others. You need to do coding. Models have been able to hit 70 plus percentage on the SW cycle for coding. Models like Claude Sonnet and then Gemini 2.5 Pro and all these models, right? So no matter what your use case is, the AI models have matured enough for people and companies to use them in production. So when that problem is solved, where are we, right? This is where the infrastructure problem comes in. So the stats I showed you earlier back up this point that even though you have your production ready, the infrastructure is not yet caught up. Here's where I want to jump into the Kubernetes part. Yes, you can write your AI app and then directly run it on your, physical servers and, your Linux OS and GPUs. But when it comes to scaling, when it comes to sort of thinking of serving thousands of users and running this at a production scale, Kubernetes has a lot of things taken care for you, right? So that's why I want to stress this point that it's not that it's just good enough for AI. It's sort of giving us this ideal infrastructure and ideal building blocks for us to do AI serving. Whenever you install, let's say, whenever you have a GPU ready server, right, you're going to install a lot of drivers and other peripheral components in order to make it ready. Yes, you need to do that on Kubernetes as well, but the process in order to do that has been really streamlined by the operators themselves. So, for example, if I'm using NVIDIA GPU, then NVIDIA officially has an NVIDIA operator Helm chart, which you can just deploy and it would seamlessly work, right? Every provider has one, AMD has one, NVIDIA has one, and so on. Then comes the auto scaling part. So this is not just for AI. This is true for even your normal cloud native applications where auto scaling is something that's inherently handled in Kubernetes, which gives you the freedom to just focus on your apps and takes away a lot of manual and hard work that you need to take care of instead, which is one of the more stronger features of Kubernetes and why it's a great choice for production grade applications. And this fact is once again enhanced and repeated just the same for AI workloads as well. So in the use case that I'll show you later in this demo is using one of the open source projects, which is Kserve and Knative. These open source tools already exist for us to handle the auto scaling bits inherently in Kubernetes, right? And of course, it works across clouds. So one of the challenges which I highlighted earlier is to make sure that the coordination and the management across clouds becomes easy. And you'll see what I mean by this when I introduce k0rdent, right? So just before k0rdent, I jump into the enterprise grade open source solution k0rdent. Let's look at what else is possible, right? When we understand the problem statement that is in front of us, first one is obviously do nothing, right? But like we saw, we'll soon get into that rabbit hole where everything becomes complex. Then there's the DIY open source solution. So open source definitely has all the components. It's great. It's one of the reasons why Kubernetes as a framework grew so much, which is because of the open source community and the entire ecosystem around it. But the challenge over here becomes when there's 5 different solutions or 50 different solutions for one single problem, which one do you choose, right? What are the pros and cons of each one? If you choose this, let's say solution E, will it work nicely with solution Z I have that is solving another problem? There's so many mix and match of tools that you have to do, which becomes the additional add-on, right? And there's a proprietary solution. Yes, it works great if you are working on only one cloud. So AWS definitely has good tools and services for AWS. Azure does for Azure, vSphere does for vSphere, and so on. But we also what happened with the VMware acquisition, right? Again, that's just a common example, and everybody will understand that, which is why I'm taking that. But even without the VMware Broadcom acquisition, we've seen so many other examples where companies do not want to get vendor locked in and face the consequences much later on. And that's where we see enterprise grade open source solutions really becoming a successful model for many companies in the past in different areas, right? And this obviously relies on the DIY open source components, but then all the challenges that I mentioned of you picking and choosing and doing all the hard work is taking care of you in the solution. And this is where I want to introduce k0rdent. So what's k0rdent? k0rdent is a declarative Kubernetes platform engineering framework, right? It's composable. It's completely YAML based. You don't have to like learn another tool or another language like you would if you choose an infrastructure as code solution like Terraform or Crossplane, right? This is completely Kubernetes native. You just have to know your YAML and Helm charts. That's it. Briefly, there are 3 components: cluster management, state management, and observability. Let me tell you about observability real quick. No matter what platform you build, however great it is, if you don't have eyes and ears onto that platform, it becomes really difficult for day 2 operations, right? That's where the observability stack comes in, where we use tools like Prometheus, Grafana, OpenTelemetry, OpenCost, and so on to give you this entire stack baked into the platform itself. So the first 2 components, cluster management, is about how you define your templates in order to describe what a cluster should look like and where it should live and so on. State management is something that you define for the services that you want to deploy. So cluster management becomes your day 0 cluster deployment itself, and state management becomes your day 0 or day 2 services deployment, right? So one of the necessary or one of the necessities or the reasons for state management is, let's say you have like 10 or 15 or 20 clusters and you have to install let's say cert manager on all of them, right? As of today you have to do it manually, which is painful. If you don't do it manually, you'll have some level of automation like shell scripting, Python, or Ansible or whatever. That entire thing is avoided. That overhead is taken away from you because you can directly mention the service that you want to install in your cluster deployment itself, which I'll show you later. Again, it's essentially the same components, but just to give you an insight of the open source about the open source world I mentioned. For the cluster management, we use the upstream cluster API, CAPI. Right? So if you all have had experience working with CAPI, it's basically the standard set by the Kubernetes SIGs in order to provision a cluster in a repeatable way. Every cloud provider has their own implementation of CapEx. So AWS got Kappa, OpenStack's got Capo, CapZ, CapV, and so on. Get the idea. right? And then there's state management, which is taken care by yet another open source project called as Sveltos. And then this is the cluster definition, which I want to show you real time in terms. All right. So our application for today, our demo for today, right? Which I'll take a use case, but this is the framework that's sort of required to make this ready. We have everything defined in a single YAML file called as cluster deployment, which comprises of the cluster template and the service template. Day zero, day zero, or the service definition. For this example of AI inferencing, we'll require all these services. GPU operator, obviously, to install the required NVIDIA drivers, cert manager for certs, Istio for services, Knative and K0 for the inferencing, right? This entire thing is defined in one single YAML file, which we'll see. Okay, so let's jump into the demo real quick. This is my terminal. And before I begin, right, let's quickly do this, and then I will apply stuff after I do this. Perfect. Now let's take a look at the cluster deployment that we defined. Yeah. So this is our kindness cluster deployment, which is a CR in k0rdent. We name the cluster deployment, and then we define the infrastructure specific things. So this config that you see is the infrastructure specific stuff, which in this example, I'm using Azure. So you'll see that I've defined what the control plane should contain, what the worker node should contain, what VM size I should use. And if I come here, you'll notice that for the control plane, while I'm using the standard A4V2, for the worker node, I'm using the Tesla T4 GPUs. And this is obviously the Azure specific credentials in order to connect with the cloud. Here's where we'll mention the cluster template. So like I said, everything is templated in k0rdent. Here's your cluster template, which tells k0rdent, hey, I want to use the standalone cluster template for Azure. And this is the version 100. And then these are the service templates. So the earlier slide that I showed you, all the components, here they are defined just in the YAML and the service spec of cluster deployment. We have the NVIDIA GPU operator, we have the Istio, we have the cert manager, Knative, and K0. Right? Now let me show you the cluster templates part, right? So this is a management cluster. Okay. So I'm using this management cluster, and I have k0rdent installed over here, where I have all the CapEx controllers. Then I have the Cosmotron, which is the control plane in order to provision the clusters. And then I have the KCM, which is k0rdent specific controllers. And here are my cluster templates. So each and every cluster template that you see over here is obviously related to the cloud, which it's prefixed with. And then you have either the hosted or the standalone method of deploying stuff. This basically points to a Helm chart that is stored in k0rdent's Git repository, which points to the upstream CAPI components. I'll show you what I mean real quick. And then there's the service templates. This is where the power of extensibility comes in. All these are nothing but, all these are coming from k0rdent's own catalog. So later on, I'll show you catalog.k0rdent.com, where all these applications are just available to your service templates. And you just got to do Helm install service template and the name, right? So as long as any application has gotten Helm chart, you can build a service template for it, and it would be referencing that. And this would be referenced in our cluster deployment. So to get us going quickly, I provisioned another cluster just before this demo so that we don't have to wait for this. But very soon we'll come back to that and check. Right now things are going on. The Azure cloud specific resources would have been already created, and now it's waiting for the control plane to be initialized, right? But we have this backup server, cluster, and let's use that, right? So I've already exported the kube config, and I'm going to use that kube config. Yep, we are in the right cluster. First, let me show you the namespaces. Now, because we mentioned all those services, k0rdent automatically takes those services after it provisions the cluster and everything is up and running. And then it creates the namespaces that are required and deploys the necessary components. So if we take a look, for example, at the NVIDIA namespace, right? And the GPU operator has done whatever it needs to do, due to which now we have our Kubernetes cluster discoverable. The GPU node, the GPU node discoverable for our Kubernetes cluster, right? And the other stuff is self-explanatory too. We have the k0 and then the k-native and so on, whatever we have specified. All right. Now, this is the context, right? To jump into the use case, what I have here is a real-time speech translation application. Let me see if I'm in the right directory. Let me swap over here. Perfect. I told about k0 earlier, which basically serves the inferences. And I have defined a bunch of inference services in here. All these three, let's take a look at one of it real quick. So this kind is equal to inference service by k0. And then I have my own application, which I've put in an image and then a bunch of parameters. So this is standard Kubernetes work. This is similar for the other two as well. So the context is KubeWhisperer takes in the audio, converts it to text. Translation takes in that text and converts into the text into the destination language. And TTS takes in the text in the destination language and converts it back to audio. So let's say you give an audio file in English, and I choose the destination language as French, then it gives you French audio. But then internally, this is what is going on. So a couple of reasons why I did that. One, there's no very good open source model that does speech to speech translation really good. There are, but I'm just saying the quality of the service is not that great. Second, I want to showcase the power of k0 itself, right? So connecting all these applications is one application called as Neural Babel, which is sort of a pipeline for this entire thing. Okay, and then I think I want to show you get virtual service. Yeah, get virtual service, and hopefully everything is good. Nothing is broken at the last moment. That's the wrong command. Let me fix that. The IP address is different. All right, everything's good. Now we're finally ready to run the application, and I have a script created here in order to showcase the entire end-to-end pipeline. But before that, let me just open up another tab and go to the same cluster and watch the pods over here. So we have all these pods: KubeWhisperer, LexiShift, and Voxraga, the three pods that are corresponding to the three inference services that we just created. And I've put this on watch, right? Now I'm going to run the script, and probably won't be able to hear the translated audio because I'm wearing headphones, but I'll walk you through it. So what it did, it got in these services. Yeah, it's doing the translation right now. It's passing through all that stages, and then it'll give me the output, right? And as you can see, in my inference service, I have mentioned that keep minimum pods as 1 and maximum pods as 2. And when the requests come in, the k0 takes this and automatically increases the number of pods for KubeWhisperer, LexiShift, and finally Voxraga. There you go. So in production, we also have observed what people do is they keep the minimum pods to 0 because you don't want to waste GPU resources when you're not actually serving requests because it's a lot of money, right? So This is the reason, but for the sake of the demo, I've just kept it minimum to 1. But ideally, in production environment, you'd keep it to 0. And the the moment that a request hits, the application will parse that and then start serving up the pod and then start serving the actual request from the user, right? And if you give a couple of minutes, right, now that the request is passed, yeah, now that the script has successfully run and it sort of played the audio in my ear, it saves the output file to this. Once it's done, it'll slowly scale it down back to 0. There you go. So that just took like a couple of minutes. And now that there are no active requests coming in case of feels that a single pod with whatever resources we have defined can handle the load, it will start terminating the other pods as well, the additional pod that it spun up. So now you can see we just have these 3 running as individual pods, just one in number. All right, so that pretty much sums it up. Just to summarize once again, the definition for this entire thing to work has been defined in one single YAML file called as cluster deployment. We define the template, the cluster template, the credential in order to communicate with the cloud, the infrastructure specific configuration, and the services that you want to deploy. It's as simple as that. And tomorrow, if let's say you want to upgrade, Cert Manager to a higher version, all you need to do is install the appropriate version of Cert Manager. Okay, I have to come back to the management cluster, right? That's our actual Kubernetes cluster, right? Just have to install the appropriate version of Cert Manager, the upgraded version, the next version, and then reference it back in your cluster deployment. It's as simple as that. And once you apply the service, once you apply the CR, automatically k0rdent picks it up and does the rest, right? So let's take a look at the cluster deployments. There you go. The one that we applied just a while ago has also come up. The cluster is up and running, and we can pretty much do exactly the same thing as before. So hopefully that made sense. And any of you who've had experience in either managing Kubernetes clusters directly using Ansible or Terraform or Crossplane or any of these different services and frameworks, see the value in having all of this in one place. And let's say you just apply GitOps principles on top of this, then you can have something like an Argo CD tracking all of your cluster deployments, all of your service templates, and constantly watch them. And the moment you want to upgrade or update, downgrade, whatever you want to do, you just need to patch that one single file and it gets applied onto your tens and hundreds of clusters. Yeah, I'd like to end the talk just by showing you the relevant links. k0rdent.io is our website. And from here, you can also explore the GitHub project that's responsible. All of this is out in the open source. And then, like I mentioned earlier, we have the catalog.k0rdent.io where we have all these services that you're quite familiar with, Kira, KubeCost, whatever, right? All of this are added as service templates here, and it's quite simple, really. So I just clicked onto any of the operators. You just need to run this Helm upgrade install GP operator. The pattern is pretty much the same for all the other services. And like I said, this is an ever-growing catalog where we've added, I think, more than 50 services from day one. And you're like more than welcome to contribute to this as well.